Good morning, sir.
Good.
Okay, very good morning. So, in the first introductory class, we have discussed that why we are doing this course and what is electromagnetic wave, and what you have seen that electromagnetic wave is basically consist of electric field and magnetic field. So, these are actually vector quantity, both electric field and magnetic field. Not only that, in electromagnetics, they are not only function of space. So vector quantity means basically it is function of space, and another thing is that it is also function of time. Okay, so few things. One is basically field. What is field? What do you understand by field? What is field? You have heard na, the term field, electric field, magnetic field. Hmm?
There is a region where the force is felt.
Okay. Other than this,
Sir, it is the reason uh, where a work can be done if we move a particle or something.
no. Field is something. So you know that basic definition of field. So you have seen that agricultural field. Field is basically a certain area, okay, certain area or space, okay. So where we can define, okay, so that let's say some physical quantity is there, let's say for example temperature, okay. So temperature is, let's say in my room the temperature is distributed differently at different point in the space, okay, in the space. So that is basically field. Okay, we can say that is temperature field, okay. So that field can be scalar or vector. So in case of temperature it is a scalar field, okay. So field is something that which is varying with respect to the space, and basically it's basically at different point in the space. So space is basically a large thing na? So in different point it has different magnitude, okay. So that is basically field, okay. and and another thing is that vector field, okay. Vector field means the field not only have a value but also have a direction. At each point, in the space, it will not only have the value. For example, temperature field, the temperature has only magnitude, it does not have any direction. Now if you talk about, let's say, airflow, airflow is a field also na. So do you consider that airflow is a field?
Yes, sir.
Okay, so it has a direction also, okay. It is not only having the magnitude, how much is the velocity, let's say airflow can be measured in terms of its velocity, how much wind is blowing, okay, or flowing, okay. So that is the magnitude, and also in which direction. So you can see, let's say if you consider a large space, you are basically sitting on a ground, but at different point, on that ground. So if you measure the direction of the flow, so direction of the flow may different, okay. So that is one of the point. And also the strength of the field, or you can say you can measure it in terms of air pressure or the velocity of the wind, okay. So in terms of that, that is basically vary with respect to the space, okay. Another thing is that, let's say if it is time varying, so at one instant of time you measure the, let's say the velocity of the wind is basically, let's say 2 meter per second, okay. But in another instant you measure that it is 3 meter per second. So basically it is basically depends upon both space, time, and also having direction. So that's why the electromagnetic is very complicated thing. So it is very difficult sometimes, it is very difficult to understand that what is going on. The main reason is basically here lots of things are involved. One is basically time, okay. And if you consider that in frequency domain, then you will have frequency, so you can write in terms of time or in terms of frequency, okay. Then it's involved space, okay. At different spatial point you will have different value, okay. So because it is a field, okay. And another thing is basically it will have a direction also, okay. So and the direction is basically, it is a property of a vector, okay. So that direction or the basically the vector quantity can be represented in a different way for different coordinate system. So for that we need to understand the vector and vector algebra and vector calculus. Okay, so because calculus is also involved. Okay, we will discuss why the calculus is involved in the calculation of electromagnetic field. Okay, so for the time being, so in our network theory class, we have discussed that what is the relationship between the linear algebra and vector. Okay, so we have discussed that what is the relationship between linear algebra and the vector algebra. Okay, so they are basically interrelated. They are not two different things, because one of the thing is that linear algebra can be easily you can say coded in computer, and it is basically easily understood. And if you understand the linear algebra, sometimes it is basically very easy to understand some of the concept in the electromagnetic field theory. Okay. So let's our discussion. So I have already discussed this during your network theory class, but I will recap some of them and introduce some of the new concept. Okay, so the how the vector transformation work, how the vector translation works. So because the electromagnetic field is basically related to the both you can say it is basically both related to the space, and also it is a vector. So that's why it is very important to understand the concept of vector. Okay, so let's start our discussion with simple 2D vector, because in the 2D plane we can easily understand and we can easily visualize the vector. So that's why we start with 2D, but that concept can be extended to ND. But in our case, for electromagnetic field theory, we basically need to go to 3D space. No, not more than that, because when you will go to signal processing, or let's say some kind of machine learning algorithm, or let's say linear regression or something like that. So in that case, you need to space, but here we are basically deal with the physical space. Okay, it is not basically hypothetical ND space. Okay, so let's start our discussion with 2D vector. Let's say you have a vector V in a 2D plane. So this vector can be represented as linear combination of two orthogonal basis vector. Now the question is, why orthogonal? Why orthogonal? Why not something else? So we can represent in other way also. The one of the main reason behind the orthogonality is basically it is easy to determine the component. When you will have the orthogonal space, then it is very easy to determine the component of the vector in that particular direction. Okay, so that's why we basically choose the system orthogonal space. Only we choose x, y, and z. Okay, so let's say you have a x, y, and z coordinates. So this is x, this is my y, and this is will be z. And this is also basically related to the propagation of electromagnetic wave. Let's say this is E field, this is H field, and this is the direction of propagation. So we'll discuss later on why it is true. So you can see that this vector V can be represented as linear combination of two orthogonal vector, that is basically x and y. So we have chosen these two orthogonal vector x and y in a 2D plane, and A is the component of vector V in the direction x, and B is the component of vector y. B is the component of vector V in the direction of y. Okay.
Sir,
So
your
your
screen is not shared.
Okay. Sorry. Okay, now it's visible. Is it visible?
yes, sir.
Yes.
Okay. So, sorry for that. Okay, so you can see that this vector V can be represented as linear combination of two orthogonal vector, that is x and y. Okay, so x is one of the vectors. So you know, in the coordinate system, in a 2D coordinate system, basically you have x and y. These are the two orthogonal component. Okay, so why orthogonal? Orthogonal means they have a 90-degree angle between them. Okay, orthogonal means they have a 90-degree angle. And another property of orthogonality is basically the inner product of two the vector should be 0. Okay, the inner product of two vector is 0 means they are orthogonal to each other. Okay, inner product or dot product. Okay, so we'll discuss later on what is dot product and how it's related to some the linear algebra space, and from the dot product how to determine the component of the vector. Let's say component of the vector in that particular direction, or basically the orthogonal component of that. Okay, so so here V is represented as linear combination of x and y, and A is the component in the x direction and B is the component in the y direction. Okay, now how to find out this A and B? So that is one of the question. Okay, so how this A and B are determined? Okay, So that is, this is basically component of V in the direction x, and this is the component of V in the direction y. Okay. Now to determine this component, we will use the property of orthogonality. Okay, or we will do the inner product. Okay, so you know what is inner product or dot product. So I don't need to specify this right now, but later on we will see some visualization that what is inner product and what is cross product and how they are related. Okay, so you can see that to find out the coefficient A and coefficient B, we have to do two inner products. At first, we are doing inner product with respect to x, both the side of equation 1, and you can see that here, if you do this inner product, then this is basically related to the component A. So this is basically related to the component A, because this inner product is equals to 0. So because x and y are orthogonal, this inner product is basically 0. Okay, and you will have only magnitude of x. Okay, so you will have only magnitude of x, or basically the distance of x. Okay, so distance of x, and you can write down that A is basically equals to x square, x dot b divided by mod of x square. Okay, so where mod x square is the inner product or the dot product of x with x itself. Okay, so it is x square is basically inner product of x with x itself. Okay, and in general this is taken as 1. In general, if it is a unity vector, if x is a unity vector, then it is basically 1. Okay, so then basically the component A is basically inner product of x with v, and sometimes we call this as a projection. Sometimes we call this is projection of vector v in the direction x. Okay, now this is very important, that projection is very important, because one of the thing is that, let's say I want to find out, let's say for example, I want to find out that what is the component of let's say x. Okay, so what is the let's say what is the component of v. Okay, what is the component of v orthogonal to x? What is the component of v orthogonal to x? So for that, this inner product is very important, that projection. Why? I'll show you later on, because that was the question in let's say last year end same exam. So many people have done it in a wrong way. Okay, so I'll show you how this can be done, and later on. Okay, now similarly you can see that B is the component in the direction y. B is the component in the direction y. Okay, and you can see that x and y are orthogonal, so that's why this inner product is 0. Now I'll give you one simple question, that is, let me write. Okay, so for example, let's say I'm giving you one vector v. V is equals to, let's say, 3x and plus 2y minus 4z. Okay. Okay, so this is vector v. Now I want to find out the component, the component which is orthogonal, to another vector, that is, let's say p. Some vector p is there. So I want to find out the orthogonal component, not the projection. Okay, not the component in that direction. Okay, so let's say, for example, this vector is, let's say, 1x plus 1y plus 1z. Okay, so I want to find out what is the component that is orthogonal. What is the component of v which is orthogonal to p? So how you will find that? What should be your approach?
So cross product.
No. Cross product will give the what is the cross product distribution. That is not the component of V. That is not necessarily component of V. At first, you need to find out the dot product. Okay, so V has two component. V has two component. Okay, one is V parallel to P and V orthogonal to P. V has two component. One is V parallel to P and V orthogonal to P. Okay, so to find out the parallel to P is very easy. So it is basically simple projection, the dot product. V parallel to P is basically the dot product. Okay. V parallel to P is basically this one. Okay. Now you can see that it has two components. Now take the inner product. Take the inner product both sides. Then this component can be easily find out. Okay. Take the inner product with respect to P. So take the inner product with respect to P. So this component will be 0 because it is orthogonal. Are you getting or not? I'll elaborate it. Okay. So you need to take inner product both the side. Okay. So take inner product with P. Okay. So this will remain. Okay. This component will remain. So it is B parallel P inner product P. Okay. So this is non-zero and this becomes 0. Okay. And from this you will get this value. Okay. So you can find out this, that this is basically how much, that is V, and how much it is the value, can you tell me?
P dot V is 1.
1. Okay, this is 1. Okay. So this is the magnitude. Now what is the unit vector of P? What is the unit vector of P? So that thing you need to define. Okay, so what is the unit vector of P? The unit vector of P is P divided by norm of P. Okay, so that is basically 1 by square root 3. So you know how to find out, that is that component of x square y square plus z square, then square root of that. Okay, so that is the distance, and it is basically 1 1 1. Sometimes I will write this way also. Okay, so it is basically this one. So this is the unit vector P. Okay, so let's write it in a small p. Okay. So it is unit vector. Okay, now this into 1 is the component of B. So now this quantity is basically this quantity V V parallel P is basically 1 by square root. So it is coming 1 by square root 3 1 1 1. Okay, so this is 1. Now this can find out that orthogonal component is basically V orthogonal P is basically V minus V parallel P. Okay, so you can do this subtraction and get the value. Okay, is there any doubt?
Yes, sir.
Is it clear?
Means, sir, after the fourth line.
Okay, which one is the fourth one? So this one.
Yes, sir. After this,
yeah.
What have you done?
Okay, so here you get that this inner product is basically 1. Okay, so this inner product is basically 1. Okay, and here from here, so what is this one? Okay, so what is this one? So this one is basically, you can say it is basically it will have two things. So okay, Am I getting wrong? No, no. Okay, fine. So you will have this V. So it will have the magnitude and the unit vector. So magnitude and unit vector, and I should take here unit vector. Na? I should take unit vector here. Na? Making some mistake.
No,
So,
sir. Means you
no,
are
no, no,
doing
no.
inner product, so
Yeah,
complete
yeah.
vector.
No, no, no.
Okay.
Inner product. So basically, in the direction P, So I should do that. P should be normalized. Na? P should be unit vector. So here, this P should be unit vector. So then otherwise, that there will be something wrong. Okay, so I have done this thing wrong. So here it is
Sir, but
correct.
by
No.
people would like correct the answer.
Yeah, so small mistake is there. So that is basically one thing, that instead of inner product with P itself, I'll need to do this inner product with this to P norm, P cap. This inner product should be done with P cap. Okay. So this inner product should be done with this to P cap, not P. So this should be done with P cap. So okay. Why? Because I am trying to find out component of V in the direction P. So P has basically magnitude, na? P has certain magnitude and the direction. Okay, so it is not necessarily unit vector. So now you will get the correct result. So here, if you do this, then you will get that what is the this one? What is this product? Okay, what is the magnitude? What is the magnitude of V parallel P? So V parallel P consists of what? So V parallel P parallel P is basically P hat into some magnitude. Let's say some magnitude is how can I say? So this some magnitude is B. Let's say B parallel P mod. Okay. So V parallel P is basically, it has some magnitude and the direction. So this is my direction unit vector, and this is the magnitude. Got it, na?
Yes, sir.
Okay, so now if I do the inner product with this with P, then magnitude. So if I do this inner product, then V magnitude of V parallel P is equals to I can do, that is basically V parallel P dot P. Okay, so this is the meaning. This is the meaning of this inner product, and this you can do it. You have to do it by yourself. Okay, so this is known. When this is known, then I can easily find out what is this vector. What is this vector? Okay, so let's do it. That magnitude V parallel P. Okay, so that is basically equals to this one. Okay, so that is basically you can say that is 1 divided by square root of 3. 1 divided by square root of 3. Am I correct?
Yes, sir.
Okay, so this, if you do this summation, so it is basically 1, and you have 1 by square root 3. So that is basically okay. So this thing is known and P is known. So P is this one. Okay, so P hat is this one. So therefore, this vector is basically V parallel P is basically, this is 1 by square root of 3, and you have 1 by square root of 3. So that is basically 1/3. 1/3 of 1 comma 1 comma 1. Okay, and then V orthogonal P is equals to V minus P parallel P, and then you can do this substitution, and then you can get the result. Let's say that is 3 minus 1/3, so that is basically 339 minus 1, let's say 8/3 x, and then you have 2 minus 1/3 means 6 minus 1 5/3, y third y, and then sorry, it is plus.
Sir, it was
And then
1 by root 3.
which one?
Said
That
that
V parallel P.
yes, sir, 1 by root 3.
Yeah,
1.
yeah. Why it is true? So I'm just rewriting it. So what does it mean? So that is means basically magnitude of V parallel P. So that is how much? That is 1 by root 3, na? Into P hat. Now this is basically 1 by square root 3, and this is basically 1 by square root 3 into 1 comma 1 comma 1. So that's why it is 1/3 of 1 comma 1 comma 1. Got it?
Yes, sir.
Okay. So it is basically multiplication is there, na? Because of that. Okay. So this 1 by square root of 3, 1 by square root of 3, they are multiplied. So that's why it is basically 1/3. And then minus 4 minus 1/3 means 12. Minus 1 is 13. Okay, so minus 13. Just 13 by 3. So this is the component which is orthogonal to P. Okay. So you get now how to find out the orthogonal component of a vector which is basically orthogonal to a particular vector. Okay, so the component of a vector which is orthogonal to a particular vector. So this is the way to do that. Okay, so let's get back to our point. Okay, so this is the way we can do. Basically, this is the way we can understand that any vector in a coordinate system can be represented as linear combination of other vector. So this idea can be extended to any n-dimensional space, but here we don't need to deal with n-dimensional space because we have a limited 3-dimensional space. Okay, so that's why this is not required, but this is in general true. In general true that if we have a vector in n-dimensional coordinate system, okay, and that is very difficult to imagine. We cannot imagine the n-dimensional coordinate system. Okay, so that is basically you can always write that vector, any vector in that coordinate system as linear combination of this n orthogonal basis vector. Okay, and the coefficient of that particular vector can be found out from the inner product of the vector with itself. Okay, so this is the way. Okay, so now it's a point to matrix representation of vector. So that in algebra or geometry we basically write down or basically denote the vector in piece of paper and write it with an arrow. Okay, draw it with arrow. But in case of or algebra, so there we basically write down in terms of vector. Okay, so you know that matrix vector. Okay, we can always write them in terms of matrix vector because this thing is basically indicate the point. Okay, so for example, consider a vector 2, 3. Okay, 2, 3 transpose or this is basically this is called column vector. Okay, the column vector is most of the cases we represent as vector, and the row vector is basically transpose of the column vector. Now this can be represented as linear combination of two orthogonal basis vectors. So here in this coordinate system, my orthogonal basis vector this basically represent x. 1, 0 is basically represent x, and 0, 1 represent y. 1, 0 represents x and 0, 1 represent y. Okay, and you have the 2 magnitude of 2 in the direction of x, and you have magnitude of 3 in the direction y. Okay, so you have magnitude 2 in the direction x and you have magnitude 3 in the direction y. Now these are basically weight. So these are basically weight. The 2 and 3 are basically weight of the vector in the direction x and y respectively. And x and y are orthonormal basis vector. Why orthonormal? Because its norms are 1. The norm of the vector x and the norm of vector y are basically 1. So that's why we call them orthonormal basis vector. Okay, so if their norms are not equals to 1, so in that case we will say that for general purpose we can say that this is basically orthogonal space. Okay, and when norm is equals to 1, so in that case we will say it is orthonormal basis vector. Okay, the basis vector or basically the coordinate system that based on which our basically the frame of reference is there. Okay, So you have understand that this vector is nothing. This vector is nothing but a point. This vector is basically nothing but a point, that is 2, 3, and that then you are basically taking the difference with 0, 0. The center of origin of this system is basically 0, 0. Origin of the system is 0, 0. So basically this vector is how this vector is coming up. This point P minus origin. The point P. So here let's say this is the point P, or let's say B. Okay, that minus the origin 0, 0. So that in that way this vector has been formed. Okay. So basically vector is nothing but a point. Okay. So vector is nothing but a point in the coordinate system. But that is basically difference with respect to the origin, because origin is the reference. So with respect to the origin, now if you shift the origin, in that case the value of this vector will change. Now if you shift the origin, so if you redefine the coordinate system in some, let's say redefine this coordinate system somewhere else. Okay, somewhere else you can redefine a new coordinate system. So with respect to the new coordinate system, it will have some different value of this point. Okay, so we'll see later on. Okay, so it is true that this is not only the unique basis vector, that main basis vector. Okay, the or the basically you can say the original basis vector x and y. So these are not only necessarily the unique basis vector. Okay, so you may have several 100,000 or infinite sets of orthogonal basis vector. Okay, so that is true. And please note that, so this is not not part of your course, but I am saying you because you need to understand. Okay, so you need to understand that why you have different coordinate system. Okay, so you need to understand why you have different coordinate system. For example, you have a Cartesian coordinate system, then cylindrical and spherical. So why do you have? So you may have, you can define your own coordinate system also. That is also possible. Okay, so because of this, these are basically symmetric geometry. This is coming basically from the symmetric geometry. One of the symmetric geometry is basically cube. Cube is symmetric geometry. Or you have a cylinder is a symmetric geometry, or you have a sphere is a symmetric geometry. Okay, so based on this symmetric geometry, we have defined 3 different coordinate system. I will see later on that how this coordinate system are defined, and you can transform from one coordinate system to another coordinate system. Okay, we'll see later on. Okay, so as I told you, so there are infinite sets of orthogonal basis vector are possible. Okay, in vector space. So for example, we consider that 2 transpose. Okay, so 2 transpose and 1 minus 1 transpose. So this is this new sets of orthogonal basis vectors. So it satisfies the orthogonality property. So if you take the inner product between them, it is basically 0. So they are orthogonal. Now same vector v, the same vector v can be represented in our new coordinate system in something like this. So you can write in this way. Okay, so you can write this vector 2, 3 in our new coordinate system. You have the component in x prime direction. Okay, so you have the component in the x prime direction, that is basically 5, 4. So the component of v in the x prime direction is 5, 4, and the component of v in the direction y prime is basically minus half. So how this component are coming? So it is basically based on our that inner product theory. Okay, so how to find out the component? So it is basically you have to take the inner product of the basis vector with respect to the vector and divided by the norm of that vector. Okay, so in that way it is basically coming. Okay, so you can understand that in our original set, what is the component? What is the component of v in the x direction? 2. And what is the component in the y direction? That is 3. Now in our new coordinate system, you have something like different. Okay, so you something different, that is 5, 4, and here you have minus 1 half. Okay, so you can understand that this is my new coordinate system. That is basically this is the new coordinate system. Okay, and you can see that in the new coordinate system, so this is basically x prime. Okay, and this is basically y prime. So you can see that y this is basically negative. You can see let's say here this is my direction of y, but the component or projection of this vector with respect to the y axis is basically in the negative direction. It is basically in the negative direction. That's why it is negative. Okay, and here it is more than 1. Okay, so it is basically more than 1. So you can see that it is basically, if you take the projection of V in the direction of x prime, if you take the projection of V in the direction of x prime, then it is basically more than 1. Okay. So from the geometry also we can understand what is going on. Okay, and also from the mathematics we can easily find out the component of the vector in a particular direction. Okay. Okay, so this concept can be extended to any n-dimensional space, and you can easily find out the component of a vector in a particular direction. Okay, if it is that orthogonal set. So if it is not orthogonal, so in that case also it is possible. I am saying that if the set of basis vector are not orthogonal, so in that case also it is possible, but it is difficult to do. Okay, so it is very difficult task to do, and you have to solve lots of more equation. Okay. Okay, so what is the meaning of inner product is basically you have to add basically the component of that vector in that particular direction. Okay, so this is that x vector, it basically consists of, this is my basis vector, so it has basically n number of element. Okay, so this is my basis vector, it will have n number of elements. If it is n dimensional space, if it is a 3-dimensional space, you will have 3 elements. So you know how to do this. Okay, so this is not a very big deal for you. Okay, so because you have already some background of linear algebra, and you have also done some courses, okay, of let's say signal processing, so that's why you have already have this background to understand this. Okay, what is inner product and what is orthogonality. Okay, and then what is the norm? So norm is basically the magnitude of this. So you have to take that, you have n number of components, so in each component you have to take the square of that and then square root of that. Okay, so that is basically the norm of that vector. Okay, and then the property of orthogonality means basically that x I, so ith vector and the jth vector will have the inner product between them is basically 0. Okay, so that's why we say that this vector sets are basically orthogonal to each other. Okay. Okay, so now move to transformation of vector. How we can transform one vector into another vector. Okay, so this is also another important property. Okay, because you know that when we will do some linear operation, when we will do some linear operation of let's say vector. Okay, so when we will do some linear operation of vector, then we can see that one vector can be transformed into another vector. So we will see later on. Okay, that is basically transformation of vector. So for example, let's say how can I say? So for example, let's say so you have a little bit knowledge of this thing, electric flux density, magnetic flux density, magnetic field, little bit knowledge, how they are related, electric field and electric flux density, how E and
Yes,
D
sir.
are related in your basic physics. You have done that course, no?
Yes, sir.
Okay, okay. So you have little bit knowledge. So that is basically we write that D, we write D is equals to epsilon, D is equals to epsilon into E. Okay. Now what you have studied, so this is basically scalar quantity, but in reality there are material exist. Okay, so you have what you have studied, so this is the scalar quantity, and that is basically epsilon naught into epsilon r, okay, and E. So you can see, so this is basically same vector with the scaling. So it is basically the D vector and the E vector. Let's say you have for a particular point, D vector and E vector are basically same. Okay, D vector and E vector are basically identical, but with some kind of scaling. So this is scaling factor. But there are certain kind of material. Okay, so there are certain kind of materials where this is not a scalar quantity, so it is a matrix quantity. Okay, so you'll have, let's say, epsilon xx, xx, then epsilon xy, epsilon xz, and so on. Okay, so then epsilon yx, epsilon zx, then epsilon yy, epsilon xyz y, then epsilon y yz, then epsilon zz. Okay. Then you have that component of ex, ey, ez. Okay. So these basically transform. This transform this E vector into D vector. Okay. So this is, they are not no longer the same vector. Okay, or don't have the same direction. So E vector, the electric field and electric flux density, so they are not same vector or pointing in the same direction. Okay, so in the, this is also possible. So this is a kind of material. So we'll see later on. Okay, that this kind of material may also exist in nature. Okay, so that's why you need to understand that vector transformation property. Okay, so how the one vector can be transformed into another vector. Okay, so this property is very useful. Now we'll start, so as it is easy to understand the 2D coordinate system, so we'll start with 2D, and then we'll see later on that when we do that vector transformation. For example, if you want to transform a spherical coordinate to cylindrical coordinate, or basically from Cartesian to cylindrical or cylindrical to spherical. So in that case, this transformation matrix is very helpful. So how this transformation matrix can be obtained? So this concept we will discuss in the proceeding class. Okay, so consider one matrix M. So M is, let's say we have considered the M is basically 2, 1 and 2 minus 1. Transform orthogonal basis vector x and y to another sets of basis vector x prime and y prime. So what it do? So this transformation matrix basically transform our orthogonal basis vector into another sets of basis vector, that is x prime and y prime. So please note that it is not necessarily that x prime and y prime should be orthogonal. Please note that x prime and y prime not necessarily to be orthogonal. Okay. But in this case, it is basically orthogonal. We are getting the orthogonal set, but it is not always true. Okay. So please note that. Now, what is x prime then? X prime is basically slicing. X prime is basically, if we slice this first vector, so that is basically x prime. Okay, and if we slice the second vector, so this is my y prime. If I slice this vector, this 2 and 2, so you can understand. So if I slice this 2 and 2, so this is my x prime. Okay, and this is my y prime. If I slice 1 and minus 1, so this is my y prime. Why? Because that x and y, if I form a matrix with x and y, so that is identity matrix. So x and y, so this matrix is basically identity matrix. So let's rewrite this. What is actually happening? So what is actually happening? So here you have x prime. Okay, so x prime is basically this one, x prime. Sorry. X prime and y prime. It is basically, you have M. M is basically 2, 1, 2, minus 1. Okay, and then you have 1, 0. This is my x. This is actually my x, and this is my 0, 1. This is my y. Okay, so this is basically identity matrix. So that's why you have this 2, 2, 1 minus 1. Okay, and this is my basically x prime, and this is my y prime. Okay, this slice is basically x prime, and this slice is basically y prime. Okay, so any doubt?
No,
Do
sir.
you have any doubt? I hope no. Okay, now we have a new coordinate system, that is x prime y prime. So how we can represent our, let's say, that old vector? So we have considered one vector, that is 2 3. How we can represent that same vector in our new coordinate system? So for that, what do you need to do? So we are considering that this vector v having ax prime component and having ay prime component in the x prime direction and the y prime direction. Okay. So it is basically you have x prime and y prime into this way. So this summation can be represented as inner product. So this summation is nothing but an inner product. Na? So you have this vector. So this vector is basically, this is a matrix. This together is a matrix. Na? This is a column vector. This is a column vector. So this together is basically a matrix, that is M. Okay, and this is basically a column vector. Now, if you multiply them, then you will get basically our new set, that is basically V prime. Okay, so then you will get, so this is basically M into V prime is basically equals to V. Obviously, it should be true. Now, to find out this V prime, what we can do? We can take the inverse of M. To find out the V prime, what we will do? We can take the inverse of inverse of M and multiply them with V. So from this equation, we can rewrite that V prime is basically M inverse. We are taking the inverse both the side, M inverse into V, and if we take this inverse, then we can find out how much is the component, that is Ax prime, and how much is the component Ay prime. So you can see that we are getting the same result. You can see that we are getting the same result what we have considered previously. Okay, so we have considered same thing, na? That they have considered that in new coordinate system. Okay, but this new coordinate system can also be obtained by a transformation, okay, by vector transformation. This new coordinate system has been obtained by some vector transformation, and from this vector transformation operator, that is M. Okay, M is basically, sometimes you can say the modifier. Okay, so M maybe. Okay, so you can see that we can get the same result. Okay, so but we have approach in a two different way. One is basically vector transformation matrix. We have considered this the transformation matrix. In the previous case, we have used our original point of view. Okay, our original point of view, that basically that vectors are orthogonal, and from the inner product you can easily find out the coefficient. Okay, so this is one of the approach, and this is another approach. Okay, so do you have any doubt?
Sir, how have you taken this M matrix? Like you have written
M
that.
matrix I have taken intentionally. I have taken this intentionally. Okay, I have taken this M matrix intentionally. So M can be anything. Okay, so why I am saying that M, how this M has been taken? So you can see that what is M? M is basically this one, that x prime and y prime. So I know that what is my x prime here. From our previous example, I know what is x prime. So what we have taken, that x prime is basically 2, 2 transpose, basically 2, 2 vector, and y prime is 1, -1 vector. So you can see that M vector is basically 2, 2 and 1, -1. Okay.
Okay, sir.
Okay, so I have taken this intentionally, so to show you that the same phenomena can be obtained in two different ways. Okay, and this is very important, because when this understanding of this M matrix, or basically the transformation matrix, is very important. Why? Because when you do the you can say coordinate transformation from one coordinate to another coordinate, if you jump, then you need this matrix. So not this matrix, so you will have some, we will derive that matrix, how this matrix has been obtained. So we will derive later on. Okay. So that's why this concept is very important. Okay. Okay, so next is translation. Okay, so there are two operation, very basic operation we do in geometry or basically in coordinate system, that is basically translation and rotation. Okay, and scaling. Scaling is another property. So translation, rotation, and scaling. So if some of you take in future, let's say if you take some robotics related course or related thing, so you need to understand this. Without this coordinate system or basically how this thing coordinate transformation are going on, if you don't understand, then it will be very difficult to understand the robotic system. Okay. So that's why it is very important for electrical engineer to take some course on vector transformation and related thing. Okay. Okay, so let's see about this translation of coordinate system. Okay, so time is almost over. Okay, you can continue for this slide and then from in the next class we will continue. Okay. So here you have the original coordinate system is x and y. The original coordinate system is x and y. Now what we did that the origin of the coordinate system has been transformed to another point. So another point. Okay, so that is basically move to point T. So T is the translation vector. T is the translation vector. Okay, so T is basically 1, 2 prime. Oh, sorry, 1, 2 transpose. So basically 1, 2. T is basically 1, 2. Okay. Now, as I move this origin of the system, then what happened to our new coordinate system? So basically our new coordinate system is basically that x prime. So here it is very useful to understand that this x prime basically indicate this point. So this x prime, what this x prime indicate? This x prime indicate this point in the coordinate system. Okay, so that is basically 2, 2. So this is basically 2, 2. Okay, so this is my point. Okay, this is basically point. X prime is basically this point. Okay, and similarly y prime is basically 1, 3. So this is the point 1, 3. So you can understand. So this is basically in the x direction it is basically 1. So this is basically unity, and this is basically this is 1. This much is 2. This much is 3. Okay. Now this is my new coordinate system. Now the point V. Okay, so the V in xy system can be represented in x prime y prime system as V prime. V prime is basically V minus T. So V prime is basically V minus T. So in the new system, it is basically 1, 1. In the new system, this same V in the new system, in the original system, it was basically 2, 3. It has 2, 3 vector. But in the new system, it is basically 1, 1 vector. So you can understand it is basically this much is 1 and this much is also 1. Okay. So this is after coordinate translation. Okay. Translation of coordinate system. Any doubt? Do you have any doubt? So here, please understand this concept. This V prime is defined with respect to this origin. Please note that this V prime is defined with respect to this origin. So basically, you are having this point V equals 2, 3 minus the origin. So basically, V prime is basically V minus the origin of this new coordinate system. V prime is basically V minus the origin of new coordinate system. But here this x prime and y prime is basically indicate the position of this point and this point with respect to our original coordinate system. So please note this one. Okay, so what does it mean? That x prime is basically mean the point. So it is basically mean the point in the coordinate system after translation. Okay, so this point has been translated here and this point is translated here due to shift in the origin. Okay, so that's it for today. So in the next day I will discuss about the scaling of coordinate system, and then rotation. Rotation is a very important thing. Okay, so rotation of coordinate system, and then we'll discuss about the coordinate transform. Okay, from Cartesian to cylindrical, and then from cylindrical to, so this thing we will discuss later on. Okay. And then discuss about the vector product, what does it mean, and what is okay. So I need to prepare some more slide. Okay, so that's it for today. So do you have any query or question? So you may ask. Is there any doubt?
No,
Sir,
sir.
how do we find this new origin of the shifted
Yeah,
system?
this is because of translation. Okay, so this new origin has been obtained by translation. Okay, so this is the translation vector. So basically I translate this origin into this point. So that is basically 1 2 point I shifted. So new system has been obtained by translation. Okay, but this x prime, what does it mean? So this x prime basically mean this point in the original system. So please note that this x prime basically mean this point in the original system, not in the new system. Okay, with respect to our original system. Okay, got it?
Yes, sir.
So yeah, please be careful here. So this v prime is basically with respect to this origin. So this v prime is basically with respect to this origin, but this x prime and y prime is basically with respect to the origin. Okay. Okay, so that's it for today, and rest of the thing I'll discuss in the next class. Okay, so goodbye for now. See you in the next class.